Started the recording.
Thank you, Mark.
Okay.
Hello, Mark. Hello, Christina. This is Kailash.
Hi.
Nice to meet you. Finally on Teams.
Yeah, nice to meet you. Sorry, I've got a lot of windows coming up. Nice to meet you. How's it going?
Good. How are you?
Yeah, doing good. Yeah. I didn't realize that this was being recorded. Is it getting shared between different groups?
Well, it gives us the capability to do that. Some people are meeting tonight. Others were watching from home because our meeting was last night or is another night of the week. But for those that don't have a meeting tonight, at least we have the ability to do this at another time so that at least they can see what was presented.
I've told people recently that there's going to be a library of things that they could offer, different content for cadets to see on meeting nights when the AE person can't make it. So this could be one of them.
Absolutely. We already had an intro presentation on the web, and Christina is our subject matter expert now on the astrophysics part of it. So I'm sure both of these put together will be a good initiative for our aerospace education.
So I'm going to cover a little bit about some facts about Webb. And if this is, I didn't realize that you guys had already had like an introduction. So if this is material that you've covered already, let me know. We can talk more about astrophysics.
I mean, there is some kind of an overlap, but we are okay with that. I mean, I want you to proceed with your presentation.
I've left lots of time for questions. So yeah, please feel free to ask any questions, and I'm happy to talk about my research in astrophysics more if there's time.
Got it. I don't know if I'm late for an introduction, but apart from the fact that you are working for NASA Ames, I don't know anything particular about you. So if you want, if once we start the meeting, if you can give a quick intro about yourself, that'd be great.
Yeah, of course. Let me know when you want me to start. It's just turned 8, so.
Yeah, it's exactly 8. So we'll give another 5 minutes. Mark, sir, is that fine or? So before we start, I just wanted to get the announcement out of the way because this presentation, Christina has told me that she's planning for half an hour and we'll have half an hour for the questions. So please keep your questions at the for the end of the meeting. So this is just an announcement. And if you have something in between the meeting, you can use the chat functionality, and I'm sure Christina will address it at the end as well. So it's 8:02 right now. Why don't we give another minute and then start? Sure, I think we can start now. Christina, over to you.
Sure thing. Okay. So I think you guys can see my screen. I just have a few windows. I'm gonna check this. You guys can still see? Okay.
Yes.
Perfect. So hi everyone. Thank you so much for joining. It's a late Zoom. It's really exciting to talk to you guys about James Webb. My name is Christina Hedges, and I work at NASA Ames in Silicon Valley. I'm a research scientist. I'm really happy to talk more about my research if you guys have any questions at all about my research. But mostly I focus on the discovery of exoplanets, which is planets outside of our solar system. I look at solar system objects and I try and understand more about them, try and characterize them. And mostly I work with NASA's space-based telescopes. I use NASA's Kepler mission, TESS mission, and Hubble Space Telescope to try and answer questions that we have about astrophysics. Because I'm really focused on exoplanets in my research, I'm going to keep most of the astrophysics in this talk more towards the exoplanet side. I do have some broad knowledge about other kinds of astrophysics that we can do with James Webb, but I didn't want to like overload you guys. So if you have questions about that, please do feel free to ask. So I'm going to start this talk with a little bit of information about James Webb, some key facts about James Webb, and why we're so excited for it in the astrophysics community. And then we'll talk a little bit about some of the astrophysics that I'm really interested in doing with this incredible observatory, and some of the astrophysics that we already do with the existing observatories and how James Webb can support us. So James Webb is infrared eyes on the universe. James Webb is this fantastic infrared observatory. It is utterly huge. I did get to see it, well, part of it while it was being built. I was at Goddard once, and it took a long time to put this telescope together. So if you were in Goddard at any point over the last few years, you might have been able to see it in the high bay. And so I did get to see it while some of the pieces were being put together. It's a fantastically huge telescope with lots of incredible engineering feats. And yeah, we just can't wait for it to get up there and start taking pictures. So this is the sort of roadmap of what we have currently, or what we have had in the past in terms of big observatories in space, like great observatories in space. Spitzer is here on the left. Spitzer was launched in 2003 and went up until about 2020. Spitzer was an infrared telescope, and Spitzer was fantastic. Spitzer really helped my part of the astrophysics community, which is the exoplanet community, by observing exoplanet atmospheres and looking to try and figure out, are planets outside of the solar system real planets, or are they false positives, which maybe I'll tell you guys a little bit more about in a minute. We have Chandra, which is an X-ray observatory, another fantastic one. Chandra doesn't do a lot of planet-based stuff, but it does some fantastic astrophysics. And then Hubble, which has been an incredible workhorse, launched in 1990. And you may know that Hubble has been serviced many times. Hubble still exists and still takes lots and lots of data. It has instruments from the UV into the near IR. It has touched all kinds of areas of astrophysics, and it's one of the best observatories we've had. James Webb is going to be as big of a leap in astrophysics as Hubble was at the time, and potentially even more so. So all of those news articles that you guys have read about the benefits of Hubble, you're going to hopefully hear lots more about the benefits of James Webb. This is a little sort of picture to give you guys an idea of the sorts of images that these telescopes see. So on the top left, there's the Crab Nebula. Crab Nebula was discovered in about 10,000 AD. The Crab Nebula here is observed by Chandra in the X-ray, and you can see it's this incredible gassy, with sort of like ejections coming out toward the page in front of you. It's incredibly high energy system. This is a supernova remnant. You have on the top right Zeta Fuci, which is a very bright star near a gas cloud, and the star is actually blowing gas away. And this is a view from Spitzer. Spitzer is looking at this in the IR and getting to know more about that gas. And then you have the Ring Nebula in the bottom left. That's a beautiful picture from Hubble. These great observatories are fantastic, and together you can combine their powers and take fantastic images like the antenna galaxy in the bottom right. When you combine all of these different spectra, you get fantastic images where you get to see cool gas, optical, and you get to see the high energy stuff in the X-ray. So that's what we have already. And unfortunately, Spitzer recently stopped taking data, but we do still have Chandra and HST. But I want to show you guys a little bit more about what James Webb can do for us and what does James Webb look like. Here's some nice pictures of James Webb. This is James Webb probably in the high bay at Goddard on the right-hand side. Maybe not. You can see the biggest striking thing is the segmented mirrors. You can see next to a person here. Yeah, that's working. You can see next to a person here, you have these huge mirrors. These are segmented mirrors. They are exquisitely designed. They each have their own actuator, which is a moving part, which is going to move each segment into alignment. And they're all covered in a layer of gold, which is about 1,000 atoms thick. We've chosen gold as the thing to coat the mirrors in because that's the most reflective material for infrared. And the mirrors themselves are made out of, now what are they made out of? They're made out of a material which is lighter than aluminium, but still extremely strong. It's not tungsten. Oh, I had a note here about what this is made out of. I'll come back to it. Very light material, stronger and lighter than aluminium. The biggest thing here is that to move all of these mirrors, it requires a lot of moving pieces. Hubble had about less than 10 pieces that actually had to move when it was deployed. Each time you have a piece that needs to move, it's especially when you have to move it while you're in space and while you're away from people who can fix it, that's a point of failure. And so James Webb is just leaps and bounds more complicated than Hubble because we have so many more moving pieces. These are absolutely necessary though, because we have to fit this instrument into a 5-meter fairing in a rocket. It's about 16 feet. Because it has to all squish down, we have to have all of these moving parts to sort of concertina everything in. Now, in astrophysics and just in physics in general, the bigger we can have this mirror, the more light we can collect. If we can collect more light, we can get better astrophysics images, we can get better spectra, we can get more information. And so we want this telescope to be really big, so it needs to collapse down to get in the rocket. You can see on the bottom here, this is the sun shield, which is going to protect the instruments and protect the telescope from all of the heat from the sun. This is supposed to be about the size of a tennis court, all told. It's like a tennis court sized observatory. It's absolutely huge. This here is just to give you an idea of how much bigger than Hubble it is. Hubble, again, so you need big mirrors to be able to take really good pictures. A bit like when you have your camera and you want to take a really good picture, you might put a really big lens on. You want a really big mirror to be able to collect lots of light. On the left, you can see Hubble next to a sort of average sized person. Webb is a much bigger mirror. You're talking, 4x in terms of area. It's hugely intense collection area. Inside, so Webb is not just a mirror, though. It is not just the fantastic engineering that went into making these segmented mirrors, which have no gaps between them to collect as much light as possible. It's also about the instruments. James Webb has lots of really great instruments on board. The 5 instruments are on the screen in front of you in terms of the sort of footprint they would have on the sky. You're seeing the Whirlpool galaxy. The Whirlpool galaxy is about 1/3 the size of the moon on the sky if you were able to sort of detect that light with your eyes. I think it's about a third the size of the moon. And so this is giving you a rough idea of how much of the sky each of these instruments can capture. So we have NIRCam, we have MIRI, we have NIRSPEC, we have NIR-ISS, or NIRS. This hardware is really, really exciting and really powerful, and they're all infrared instruments. So we have NIRSPEC, NIRS, and NIRCam. NIRSPEC is going to be taking near-infrared spectra. We've got lots of cool things that are unusual and new. For example, this is a multi-object spectrograph, and this is the first time that we've been able to do this in space, so that's a new leap. We have NIRS, which is the slitless spectrograph. That's going to be really important for observing exoplanets. We'll get to that in a minute. We have NIRCam. That's going to be really good at taking great pictures. And then we have MIRI. MIRI is a mid-infrared instrument. This is as far in the infrared as we'll be able to go. It's really, really important that we put these instruments into space. You can see the visible over here. The visible is where we will have light that's going to be transmitted transmitted through the atmosphere. It's going to be able to reach your eyes. If you want to observe in the visible, it'll go through the atmosphere and you'll be able to have any kind of ground-based observatory that you like. You'll still get some contamination, but if you want to observe in the visible, you can do it from the ground. If you want to observe in the infrared, the atmosphere absorbs, and unfortunately from the ground, you just can't take these pictures. The atmosphere is opaque in the infrared. And so unless you go really, really far out, you need to be in space if you want to be observing in these regions. That's why we have to get a big, powerful telescope and we have to put it in space. So these are the key instruments. I want to talk a little bit about spectra and why that's important. So you may be already very familiar with spectra. You may be very familiar with what these are, but I'll just cover it quickly. You can see on the screen, this is an image of space, of a particular part of space. I don't think I have the notes on exactly which place this is. I don't think I have it in my notes, but let's say this is a star. This picture is something that you might be more familiar with. This is a picture of space. This might be what it would look like through a telescope just to your eye. There's more interesting information that we can get out of this image if we're able to take the image in multiple wavelengths, if we're able to look at it in bluer light, redder light, infrared light, maybe UV light. We'll be able to split this into lots of different images. And some of those images, this source, the source in the middle, may be very, very bright in the blue and very, very faint in the red image. And that's telling us something really important about what kind of source this is. If you imagine taking lots and lots and lots of images at all of the possible wavelengths and taking a look at just one pixel on the inside, like in the middle of this star, what you would end up with is the brightness of this star as a function of wavelength. And that might look something like this mock-up spectrum on the left-hand side here. Here in our sort of toy example, we've taken images in the blue and we've looked at how bright is this dot, and we've looked at it in the blue. And then we've moved and changed the image and looked, what does it look like in green light, in yellow light, in red and orange? And that has given us this spectrum. And you can see in our toy spectrum, there are some wavelengths, some colors, where the star gets very faint, which is causing these stripes. This is incredibly important in astronomy, and this is how a lot of our astronomy work gets done. The composition of, for example, exoplanet atmospheres is buried in this spectrum. These emission or absorption lines are kind of blueprints for the elements, for the molecules that make up something important about our source. We can also use it to learn more about stars and the temperatures that they are. We can learn more about the objects inside the solar system using spectra. We learn more about galaxies and how far away they are. There's almost nothing that can't be better understood by taking spectra. They're important across astronomy. So this is something that 3 of the instruments enable, and the NIRCam is the one that takes most of the pictures. So where is Webb going to be? Webb is going to be, so in this schematic here, this is the sun down here, and then here's the Earth. Webb is going to be at a point called L2. This is a Lagrange point. You're probably familiar with these if you're doing lots of aerospace engineering. So in this Lagrange point, the object, whether it be a telescope, the telescope can orbit around this Lagrange point, and it is stable. It balances the forces of gravity of the sun and the Earth. And so you can orbit this point very stably. And that's exactly where James Webb is going to be. James Webb is going to be there because we need to try and get away from contaminating light from both the sun and from the Earth and the moon. We need to be far away from the Earth and the moon because they scatter light into our detectors, into our telescope. We don't want that. We want to be far away from the sun for the same reason. We want to be far away and cool. We don't want to have any scattered light coming in. And then we're going to be able to point with our solar shield pointed back towards the sun. I think that's all I want to say about L2. Okay, so what's it going to look like when we're up there? On the left-hand side, you can see the sort of observing side of James Webb. So we're going to have this mirror, and this will be pointed towards our target. This secondary mirror here will be pointed towards the target. And on the bottom, we have this solar shield. You can see it's a set of 5 layers. This is what's going to protect the primary mirror, the secondary mirror, all of the instruments that need to be cooled. They're all going to be on the back side of this telescope. That shield is what protects them and keeps them cool. Now, we're going to get to this in a moment, but the whole point of an infrared observatory if you are anything that has any kind of temperature, that's me, you, the desk, the computer, the air, anything. If you have temperature, if you have heat, you at some level emit in the IR. And what this means is that if you want to observe in the IR, everything needs to be really cold. And the further into the IR you go, so if you're trying to use MIRI, that mid-infrared instrument, if you're trying to use that, you need to be very, very cold, because to MIRI, almost anything is bright. MIRI is looking really far in the infrared, and so if you are, 100 Kelvin, you'll be really bright to MIRI, and that will completely wash out any information that you can get from your target. All this to say, if you want to observe in the infrared, your telescope has to be cold. So James Webb has the sun shield, which is keeping it cool, keeping it away from the glare of the sun. But it's also, some of the instruments, really its MIRI, are cooled actively, not just passively, but actively cooled with basically a fancy refrigerator. So we have those two sort of dual strategies. We're going to passively cool it using the sun shield, keep it in the shade, and we're going to actively cool it with a sort of refrigerator. Right. When Webb gets up there, it's going to go through an unfolding sequence. So Webb was packaged up and put into a ship, and then it was sent through the Panama Canal up to French Guiana, and it's now sort of going through the pre-launch phase. Once we get to the launch phase, and once it gets up there, it's going to go through some deployment, which is on the way to L2. The deployment is going to do things like tension the sun shields out. Once we get to L2, there's going to be some unfolding of mirrors and secondary supports. There'll be a long time where once we're at L2, we're just commissioning. Now, this happens for every telescope. We have some commissioning time. The commissioning time for James Webb is probably going to be about 6 months. During that time, we will get at least one unfocused image. And then most of the commissioning is taking images and checking that all of the instruments work, all of the focus is right. And then after about 6 months, we're going to be able to take science images with the telescope. Cool. So how do we talk to Webb? This is important. This is important for every spacecraft, every space telescope. You need to be able to talk with the Earth. James Webb will take fantastic images. Fantastic images have lots of pixels, and it means that you have to downlink lots and lots of pixels from space onto the Earth. And that can be expensive and difficult, and so we have this network, the Deep Space Network. The Deep Space Network is a set of very large dishes, and those dishes are able to downlink data from all of the space-based observatories. One thing that I kind of wanted to show you guys, but then it will stop me from doing the presentation. So remind me at the end, but there's a nice website where you can go and look and see what the DSN is talking to right now. And I checked just before this talk, and right now the DSN is talking to Voyager, which is always nice. So James Webb will use that Deep Space Network to get all of its data down onto the ground where astronomers can look at it. So Webb is a huge collaboration, people all over the world, some key parts. There's lots of countries being involved. Just to name a few: Austria, Belgium, Canada, Denmark, France, Germany, Ireland, Italy, the Netherlands, Spain, Sweden, Switzerland, and the UK, which is where I'm from, so that's nice. Also on this map, so James Webb will be controlled out of Maryland. And then there's STSCI, which is in Baltimore over here, which is going to be in charge of storing all of the data. STSCI is the Space Telescope Science Institute. So huge collaboration all over the world, but NASA is the one that is responsible for the James Webb mission. Webb's going to have lots and lots of exciting discoveries. We're talking, early universe, taking more pictures like the Hubble image of the deep pictures of the universe, looking at galaxies that are just hundreds of squillions of parsecs away. Got galaxies, looking at star lifetimes, and then crucially, this bottom right quadrant is what I care about, other worlds. So we're now going to go back. I'm just going to take a step back, and we're going to ask the question, why do we study infrared light? And I wanted to put this in because it's important. Here are two pictures of two animals in the visible light. And if you add in a little bit of extra information by taking this image and looking at it in the infrared, you see this. In the infrared, the meerkats are really bright and the crocodile is not bright. And the reason is meerkats are warmer than crocodiles. And you can tell that if you just look in the infrared. This is why we need to look in the infrared for all sorts of astrophysics. It's telling us something really important about temperature, usually, and it means that we're able to look at different temperatures of objects. So, for example, if we want to look at dust disks around other stars, if we want to look at the debris, the cruft that is around stars, and that's the stuff that new planets might form out of, if we want to look at that, it's very, very cold, and so it'll be quite bright if we look at it in the mid-IR, but it will not be bright if we look at it in the optical. If we were to take this image, for example, and we were to go further into the IR, eventually the crocodile would become bright. If we go far enough into the IR, where we're at a temperature that the crocodile is emits the infrared light. Okay. So this is the electromagnetic spectrum, and this is the visible portion. This is the part that will go through the atmosphere. If we want to observe in the visible, we can do it from the ground. Sometimes it's very beneficial to look at it in space for other reasons. We have the UV over here. Hubble can do some UV. There are a few other instruments that can also do UV, but actually not very many. This is Spitzer over here. Spitzer was very, very far in the IR. Originally, it was a cooled instrument, and then the coolant ran out, and it could only do a sort of warm version of Spitzer. And then this is the James Webb Space Telescope, so we're going to be able to cover a large portion of the infrared spectrum. This is an example of what Jupiter looks like in the infrared. Here we're looking at, again, this is about temperatures, and here we're able to see different parts of the cloud structure in Jupiter. Now this is actually a ground-based image. This is actually, I think, from Gemini. But James Webb is going to be able to take images quite like this, and it's going to be able to take spectra of objects within the solar system. And so we're going to be able to gather much more information about the atmosphere of Jupiter. We're going to be able to look at Kuiper Belt objects, get a really broad picture of what's inside of our solar system with hopefully beautiful images. But the thing I care about is that infrared light will help us find and characterize the planets that are around stars outside of the solar system, extrasolar planets, planets that are around other stars. On the screen, I'm showing a video here. This is HR 8799. This image is fantastic. This is an incredible image. It's actually a video. Hopefully you can see these moving dots. The star in this system is in the middle here, and this star has been blocked out by what's called a coronagraph. It's essentially a sort of dot. The coronagraph is blocking all of the light from the star, almost all of it. And then the light that remains is the light that's coming from the planets that are orbiting the star. And if you watch, you can see these planets going round the star. So, I mean, this is fantastic. This is incredible. You're seeing light from planets around a star that's outside of the solar system, and 20, 30 years ago, people would not have believed that there were planets outside of the solar system. There was no evidence that there were planets outside of the solar system. And now you can see movies of them going around. So this is from a ground-based telescope, and these images, the images that made this movie, have been taken over many years. And it's taken years and years to make just this small movie of them just moving a few degrees around the star. So James Webb will potentially help us find more systems like this and image more systems like this, because it's an infrared instrument, because we're going to have lots and lots of collecting area, big telescope, and we won't have any interference from the atmosphere. This isn't the method. This method is called direct imaging, where we can take a picture of planets. This isn't the method that I use. I use something called the transit method. I'm going to show you that now. Okay. Hopefully this plays. Right. We may go through this video a few times because it goes quite quickly. So in this instance, we have a star in the middle. Let's pause it there. So we have a star in the middle of the video, and then we have these 3 planets that are going to go around the star. And in this case, imagine that this is a star that is so far away that you cannot, what we call, resolve the disk of the star. As far as you're concerned, this star is so far away that it is a pinprick, and you can't see that it's this round disk. Because it's so far away, what you're going to see is you're going to see the light from this star, and it's going to be constant. It's going to be just a constant value. It's going to be the brightness of the star. And then when a planet goes in front of it, you're going to see the brightness will dip a little in this star. And then when the planet goes away, it returns back to its normal brightness. We have a few more planets now going in front of it, and they cause the brightness to dip again. Each of these events are called transits. It's hopefully going to go around now a second time. Oh, no, it's not. We'll play it once more. So each of these events are called transits. The depth of this transit right here, I'm going to pause it. The depth, how much fainter the light from this star gets, is related to how big the planet is compared to the star. If the planet was the same size, all the light would go away. And if the planet is about half the size in terms of area, then about half the light will go away. So what we can do is we can use the depth of that transit, that event, how much fainter the star got, we can use that to determine how big is the planet. I'll keep playing this. This is a method that we have used a lot in exoplanet science to detect exoplanets. This is something that was used extensively by the Kepler mission. The Kepler mission you may have heard of, it's been in the news quite a lot. The Kepler mission was fantastic, launched in 2009, went for about 9 years, if I remember right. And that mission was something that I actually worked on while I was at Ames. I was part of the guest observer office for NASA's Kepler mission during its second phase, the K2 phase. I wanted to show you guys some real data. I find that real data is the most compelling thing, especially as someone who uses data exclusively during their research. This is real Kepler data from that mission that I worked on that does this transit method. These are transits from Kepler 11. The black points are real brightnesses measured of that star, and then it has it has 6 planets around it. Each of these dips indicate that there is a planet going around that star, and then we observed for about 4 years, and then these dips keep coming back around and around as the planets orbit the host star. You can see that some of them, so this one is quite shallow, this one is a little deeper, so I know that this planet is bigger than this planet. And then this one is bigger than one. So this is a method that we use to detect exoplanets. Here's a little roadmap of missions that look at exoplanets. Now we have Kepler here, which is the mission that I was just talking about. Kepler, unfortunately, we ran out of fuel, and so we closed out the mission, but now we have the TESS mission, which is a sort of spiritual successor to Kepler. Spitzer was in this picture, and before that, Hubble. Now, the thing about Kepler and TESS, these two are about finding exoplanets. Hubble and James Webb are really, in terms of the transit method, more about understanding exoplanets. So Kepler and TESS can point out those stars, they have planets, they have an orbital period or a year that's this long. You have to look at this time in order to see them. But Hubble and James Webb are much more about looking at particular planets and asking questions, what are the atmospheres of these planets really like? So I'm going to play another video now. So before we had that transit method where we had a planet that was going to move between you and a star, and it was going to reduce the brightness. Now we have a planet with a little atmosphere around it. So here we have an atmosphere, and it's done in green. This atmosphere, it goes around the planet, and in 2.1 microns, this atmosphere blocks a little bit of light. And what that means is it's going to reduce, it's going to make that brightness reduce of the main star a little bit. If we go into the next waveband, we'll let it play. So here comes the planet. In the green, it reduces the wavelength just a little bit. In 1.8 microns, the atmosphere is a bit more opaque. And what that means is it's blocking more light of the star. There's some molecule in the atmosphere which is blocking more light. It's absorbing more light. The atmosphere appears thicker. And that means that the transit depth gets bigger because the planet looks like it's a little bit bigger. And then if we keep playing, the yellow one, it's even thicker. It's a bigger atmosphere. It's absorbing more light. There's some molecule in it which is stopping the transmission through that atmosphere, and it's causing a really deep transit. What we can do as scientists is we can say, if we know the transit depth in these different wavelengths, we can use that, look at our knowledge of what molecules absorb what light in which wavelength, and we can put those two together and answer the question, what must the atmosphere be made of in order to cause these different transit depths? Now, here is a pretty recent, I think this is a 2019 result. This is a spectrum of an exoplanet atmosphere taken with a smorgasbord of different instruments. For example, this is probably ground-based stuff, this is HST, and these 2 points are Spitzer. This planet has been observed with lots of different instruments, and it's been observed for hours and hours and hours. It's been probably, it's cost a lot of observational time to really get this deep dive. The reason being, these atmospheres are incredibly tiny. We're talking, a little sort of a tiny layer around an already tiny planet. And so we need a lot of time to be able to collect enough photons to get this information. But the thing that you can see, particularly if you look here, which is the HST portion of the data, is this is the change in transit depth. So this is how deep of a bump, how deep of a dip did that planet have at different wavelengths. And this wavelength here, it's in the near IR. You can see that there's this bump right here, and that's really indicative that it's water that's causing some absorption here. What this spectrum shows is that there's water in the atmosphere of this planet, and this planet I think was WASP 127. So yeah, in this planet it's got a layer of water in the atmosphere, and we know that pretty well now. Now, this region is the region that HST can unlock. This region is the region that James Webb can unlock, and crucially, James Webb can go to much smaller planets. Because James Webb can go to smaller planets, and it doesn't need quite as much time to be able to do it, James Webb is going to be able to do a huge survey of lots of different exoplanet atmospheres, and we're going to be able to build up a picture of what these atmospheres are really made of. And now you can see, for example, here, these 2 Spitzer points, they are telling us something. They're helpful points for our models, but James Webb will be able to get hundreds and hundreds of points in this spectrum, will be able to resolve these features. And that will really be able to tell us whether things are, for example, CO2 or water, whether carbon dioxide or water, and it'll be able to help us distinguish clouds or clear atmospheres. So James Webb is going to really unlock lots of new information, particularly on small planets for us. This is sort of telling you a little bit more about that, or it's kind of drilling that home. We'll be able to look at, is it oxygen, water, carbon dioxide, methane, which is a really common common molecule in the atmospheres of exoplanets. So we'll be able to look at all of these different molecules in one spectrum from James Webb. Now, James Webb won't be able to take a transmission spectrum of something that looked exactly like the Earth, something the size of Earth, with a year that lasted 365 days, with a temperature which was about the temperature of Earth. Unfortunately, even James Webb is not powerful enough to be able to detect that. We're going to have future instruments to be able to detect something like that. But it will help us build a picture of warmer planets, maybe slightly bigger planets, and that will help us understand more as we push down to try and get towards that detection of Earth-like planets in habitable zones. So that's what I'm the most excited about, is this understanding of exoplanets, exoplanet atmospheres, how do we detect them, characterize them. So I'm going to leave it there. I think we have lots of time for questions. Please feel free to ask any questions and I'll be happy to answer them. I'm going to stop sharing. And I think I don't have a chat, but I can see if I can find the chat if there's any questions. Or hands up is great as well.
Yeah, you could either use the hands up or the chat functionality, and I can relate.
Yeah, absolutely. Would you be all right to call on people to ask questions?
Sure.
Thanks.
Sure. I'll first go with Colonel Kenneth.
You mentioned that you were going to provide us a link of what probe the DSN is communicating with. Yeah,
let's do that now. Okay, hang on. Let me get my presentation is still up on my computer. So let me get my thing. There's the DSN. Okay, I've got to reshare. Stand by. Stand by. This should work. Can you see Can you see this? It's a screen with dishes. Can you see it?
See the dishes.
Yes, fantastic. Okay. They're not talking to Voyager anymore. That's upsetting. So this is the Deep Space Network now, which is this interface. Unfortunately, it looks like there's not very much exciting going on. But honestly, like an hour ago, Voyager was talking to the Goldstone dish. You can see this one is talking now. So they're talking to Mars Odyssey. That's kind of fun. That's kind of cool. So this dish here, which is part of the Canberra, which is the Australia set of dishes, is talking to Mars Odyssey. That's Mars Reconnaissance Orbiter. It's a shame that they're not talking to Voyager right now. But if you're interested, you can go to this website and you can see what we're talking to exactly now. I've seen some really cool stuff, some stuff to look out for. We really had a kick out of looking at this when my previous mission, Kepler, was sort of going through its last phases. We had a kick seeing the DSN talking to it for one of the last times. We had a kick out of seeing it talk to TESS, which is this new exoplanet mission, for the first time. That was very cool. But yeah, this is a great place to sort of see what NASA's talking to right now.
Thank you.
Oh, I think you might be muted.
I'm sorry, my question was, can everybody access that site? Is it open to the public?
Yeah.
Or?
Yeah, if you Google DSN, Deep Space Network, it's like the second link. It's the DSN now. And you'll see.
I posted it in the chat.
Richard has already posted us a link. So thanks, Richard. So the second hand that is raised is Second Lieutenant Ahmed. If you could unmute yourself and ask a question, please.
Hi, you had mentioned how Webb has a system to protect it from heat, specifically heat and light from the sun. What sort of protection systems are in place for more physical issues, space debris and such?
That's a really interesting question. So this is a really good question. There are, if you ever go to any of the NASA visitor centers, sometimes you can see bits of kit that have come down from space. If you go to if you're ever at the Smithsonian, they have stuff that's come down from space, and if you look at it, you can see that it's covered in little holes from micrometeorites, which come and they hit the instruments. They hit the stuff, the sort of housing that the instrument's in. Space debris is really a problem for some instruments, especially because everything's whizzing around so fast. The smallest speck can actually drill big holes in pretty dense material because it's got so much energy in it. The nice thing about going to L2 is that this sort of human-made debris that is all around the Earth from things like spacecraft collisions and bits coming off of different orbiters, that stuff is not at L2. L2 is far enough away that it's pretty separate from all of this human-made debris. Now, there's another sort of question embedded in that, which is, well, what about not human-made stuff? What about stuff that's like solar system objects? What about meteorites and stuff like that? Those sorts of collisions should be incredibly vanishingly rare. And we have people like the planetary protection folks who are tracking lots of the non-human made debris, all the sort of micrometeorites, the meteorites, all of the asteroids. We're tracking those, and so we should know if any of those come close to any sort of collision with Earth or anything that Earth cares about. So that's the benefit of being in L2. There shouldn't be a lot of debris.
It almost sounds like that L2 has an almost a Jupiter shielding for the rest of our solar system, where Jupiter and their moons has a lot of protection from some of the inner planets from what's happening outside.
Yeah, that's a really good point. Jupiter does do a lot of this sort of sweeping up of stuff. And so we are very protected from stuff in the outer solar system by Jupiter and Saturn. They tend to, their sort of orbits tend to carve out paths and keep everything in the inner solar system pretty safe. Is L2 protecting us? It's true that the Lagrange points definitely can end up also having that sort of effect of like stuff gets trapped in L2. There are other Lagrange points, there are 5 Lagrange points. So there's ones in front of the Earth, behind the Earth, on one side, on the other side, and then one on the back side of the sun. That it is true that stuff can kind of collect towards those points. Yes.
Thank you.
So next up, it's Major Mark Friedel. Before I pass it to him, I just wanted to thank him for organizing this presentation as well at a big level. And between me, Mark sir, and Captain Spears, we made this happen. So special thanks to him. So go ahead with your questions, sir.
Yes, I understand that the lifespan of this mission is about 5 to 10 years, whereas Hubble has been going on since the early 1990s. What is the limiting factor on the lifespan of this mission?
It's almost set right. So great question. Yes, James Webb has to last 5 years. Like we've said, it must. We've designed it so that it will last 5 years. And the ways that we've done that is we've got things like redundancies. All the cameras basically are 2 cameras. And if one drops, we'll turn the other one on so that we don't lose image quality. We'd like it to last 10. And the idea is that folks at NASA Goddard are going to be making sure that they're going to be making a lot of decisions to make efficient uses of things like propellant and coolant. Once we're at L2, these are things that like move the observatory and things that keep the instruments cool. But ultimately, it's going to be those expendables that probably stop that mission lifetime. The other part, it's not just like a coolant and propellant, but also there is a finite lifetime to some of the parts, and as things live in space for too long, these parts and these things start to wear, moving parts start to wear, and so it may be that things like reaction wheels and stuff like that are the things that go, but it's probably going to be coolant. It's probably going to be coolant that we run out of. But hopefully not for a very long time. People are making efficient decisions about how to spend these resources so that the observatory can last as long as possible.
Thank you.
So I do not see any other hands raised. Any other questions in the pipeline?
If I may ask another couple
Sure.
of questions.
Yeah.
Sorry, you can certainly shush me if somebody else raises their hand. What do you think is the most probable point of failure that may halt this mission before it begins?
James Webb,
Yes.
you guys are recording this. I don't think I want to say on a recording. No. Okay. What's gonna tank it? Well, there's lots of big pieces that have to go right for James Webb. The sun shield has to deploy, and now I'm no engineer, so I don't know which of these big pieces is the most likely to fail. Obviously, NASA has an incredible success rate in getting these amazing missions to work, but right off the bat, the sun shield has to deploy. If we can't have the sun shield, we can't have anything, pretty much. The mirrors, all of the actuators on all of the mirrors have to work. So those all have to go into place. And it's just that there are a lot of them. As I said, Hubble had less than 10 moving pieces, but James Webb has hundreds of moving pieces, and they all have to work. So if you really twisted my arm and I had to say what was not going to work off the bat, or what was going to tank the mission, it would be tanked if one of those things did not work well. Having one instrument not work would be terrible, but they all have so many redundancies in them. It's going to be something like, something like the sun shield didn't work, or the segmented mirrors didn't go into place. But that hopefully won't happen.
And what would you say would be a success that would make all of this effort worth it? What would be the thing that everybody would be able to say, we did it, and pat themselves on the back? Like, what would that success look like?
So it's really interesting because James Webb James Webb is an instrument that every astrophysics community thinks is their telescope. So everyone in my community of understanding planets outside the solar system believes that James Webb is a mission that understands planets outside of the solar system. But if you are someone who cares about high redshift galaxies, you probably think it's your mission. You know, it's going to do something incredible and revolutionary in your field. The only thing I'll say is exoplanets, my sort of field, has gotten about a quarter of the James Webb time so far. So the way that James Webb currently works is that we have early release science. This is like guaranteed science that we're doing basically day one. You know, the first part of James Webb is going to be these kinds of science. We've already had a guest observer call, which means observers like me have asked for time and they've said, oh, I want to observe this planet or I want to observe this galaxy. Please give me the time. And that first cycle has been proposed for and allocated. So basically, we know already what James Webb is going to look at in this first round of observing. About a quarter of that time went to planets, which is huge, huge. And so for me, the thing that I would say is that if James Webb gets up there, turns on, takes an observation of the atmospheres of planets, and then takes a look at what Hubble saw and sees something that's like much higher resolution, and we can sort of see the kind of blurry spectrum that we took with Hubble, and then look at the high resolution, fantastic one with James Webb. If we can compare those two and sort of see that Hubble did it right and James Webb can do it better, that will be huge. So I'm the most excited to basically see these exoplanet atmosphere spectrum in full resolution and check that what we say we saw with Hubble is exactly right. That's where I think it will be worth it.
Thanks.
Any other questions? I don't see any other hands raised at this moment, but I do have a couple of questions for you. And my first question is regarding the telescope itself. How is it powered? Are we using solar power or are we using RTGs?
Yes, we're using solar power. So that sun shield has the bottom facing towards the sun. That's the hot side. You can put as many solar panels as you like on hot side because it doesn't matter if those get warm. So we have a big strip of solar panels on the back side, and that'll pretty much always be facing the sun. So the telescope always has power.
Sure. And when you mentioned coolant, right, I wanted to actually know what is colder than space itself. So how do you choose a coolant that is actually colder than the ambient space?
Yes, and so it is not just ambient space. So the thing that potentially for the coolant, the thing that is warm is the instruments and everything itself, like the telescope, the whole telescope gets kind of warm. And MIRI, the mid-IR instrument, is so sensitive that just the heat of the telescope, just the heat of the instruments itself from all of the sort of the heat kind of moving through the telescope, that's enough. And so it has to be isolated and cooled down to, and I had the number here, but it has to be cooled down to tens of Kelvin. Mm-hmm. Space itself is like, if you go, you know, to the blankest void of space, is about 4 Kelvin. So it's very hard to cool cooler than that. I think it's been done on Earth, but we don't usually need to be cooler than that because you can't, there's no point. If you were to take a picture, it'll be basically.
Yeah. I mentioned that question because RTGs generate power using the cold side in the space. So I thought, like, what is going to be more cold than space itself? Exactly.
Yeah. No, so we cool it to, I want to say it's like, don't quote me on this, it's like 50-ish Kelvin is what MIRI is to.
Got it. My other question was to do with exoplanets.
Yeah.
So I know there's a lot of excitement in discovering a new exoplanet, and you actually assigned the name of the, whoever found it, you assigned the last name to it, if I'm right.
No. So that would be nice. No. So when you discover planets, people ask me this a lot. So discovering planets is fun, and it's something that it is possible to do as like an amateur astronomer. It's definitely possible to do. There's lots of resources about how to use existing archival data to go hunt and look for more planets. I can definitely point you in the direction of where to go read about that.
Sure.
When you do that, the planets get named after the mission data.
Okay.
So I found a couple of planets So the ones I found in K2, they're called like K243C and further. And then ones from TESS are called, they're actually called TOI, which is Test Object of Interest. So it's TOI something 2076. And that's sort of where they start. They can also end up being named after their bigger names, like the host star name. So one's around, so there's a star 55 Cancri, and that has planets, and they're named 55 Cancri, B, C, D, E. So unfortunately, you don't get to name them after yourself. There are no planets called Christina.
Thanks for clarifying that. I mean, this is something I read offline in a lot of forums, so it's actually better to ask straight from a NASA employee. How does it actually work? So thanks for clarifying that. My final question is, yes, you have observed a lot of exoplanets. What is the next step after finding them? You just name them, and what is NASA's next initiative like once you have an exoplanet already found?
Yeah, it's a really big question, and it's something that if you're a researcher, you have to defend this point a lot, especially to people who are outside of exoplanets, because why should you get all the time? Like, you're just going to find them, and then what? Like, what are you going to do with them? And so some of the answers to this question include, once you find a lot of them, you can start to do demographics. You can understand, for example, how likely is it that you would have an Earth-sized planet around a given star? What sort of orbital period do planets have? You know, do they have a year that lasts 10 days, 100 days, 1,000 days? You can start to ask those demographic questions. Those are really important if you want to answer the question, are we special? Is Earth special? If Earth is very, very special, that's informative for NASA. And if it's not, that's also hugely informative. Right now, Kepler has discovered thousands of planets, and TESS will discover thousands more. But it's very hard to get to Earth-sized planets, because they're very, very small, around sun-like stars at 365-day orbital periods. It's very difficult because the signals from them are incredibly tiny. So right now, we do a lot of work in shorter period planets or bigger planets, and that's helping us understand those demographics. The next sort of things that we can do is characterize individual systems, like with the atmosphere characterization that we're doing. That's going to tell us more about, well, are they cloudy? Are they do they have hazes in them? Do they have some sort of reprocessing in them? What are they made out of? Do they have water? Maybe watery atmospheres are really, really rare. It kind of seems like not, but that's maybe another point. So there's understanding demographics, there's understanding what they're made out of, what their atmospheres are like. And that's all helping us answer the question, what is Earth special? What's our place in the universe?
Fabulous. So I know you're not from the astrophysics, like from the origins of the universe, like that's one of the research goals, right? If you know something, you can please highlight on that. I know you're the exoplanet specialist, but I'll still get your opinion on that. Yeah,
now you're pushing right at the barriers of my knowledge. I wouldn't like to comment too much on this, but certainly the thing that Hubble can do is, or the thing that a person can do if you have a telescope and you can look at a patch of sky and you can do a really deep image, is that you can see galaxies, and these galaxies will be redshifted. So now redshifting is what happens when you have an object that's moving really, really far away from you, and it's moving fast away from you. It's a bit like if you've, when a car drives past you and it's sort of coming towards you, and it'll, if it's a car with a siren on it, it'll sound really loud and high pitched. And then as the car goes past you, the siren sounds low. Yep. Yeah, that's exactly what's happening, but it's in light. And that shift as it's moving away from you and it's moving really fast causes the galaxies to go into redder light. My layman's understanding is that James Webb is going to be able to look at deeper images, higher redshift galaxies, and it's going to push our understanding to earlier times in the universe. It's going to look at higher redshift galaxies, which are older galaxies. So we get to look at galaxies that are from closer to, more towards the beginning of the universe. Sure. And one final question from me is, how does this telescope compare with a radio telescope? How are the science accomplishments different when you compare it to a radio telescope? Yeah, they are very different. Radio is largely done from the ground. I can't even think of a space-based radio telescope. So radio is a thing that you do from the ground, and you have huge facilities like SKA is Square Kilometer Array is one of the bigger upcoming ones. SKA, am I right about that? So that is a observatory that would be a huge kilometer-sized facility with many dishes in it. And the nice thing about radio is that when I said that Hubble has a smaller mirror than James Webb, and so James Webb will be able to collect more light, the nice thing about radio telescopes is the size of your mirror is the size that you can like put two telescopes apart. And so the bigger your facility, the bigger your sort of telescope resolution is. And so radio is really like this whole other realm, because you're no longer interfering with the atmosphere in the same way. You have big ground-based facilities, so they are very different beasts.
But do they contribute to the same science goal in two different ways?
They can do. So I don't know of any, and this is potentially my naive understanding, but I don't know of any exoplanet results that have been big in the radio.
Right.
But certainly for galaxies and for that kind of astrophysics, there's huge parts of the radio which are very, very interesting. And I think having radio, optical, X-ray, all of these together paint this picture of the energy in the universe.
Yeah. So I was lucky enough to interact with the folks in the Apple Valley Radio Telescope facility, and they are complementing the Juno mission for Jupiter. So the atmosphere of Jupiter and stuff like that, they're validating those results with the radio observations they are making. So that's pretty cool. So that's why I asked you that question in the first place.
Yeah, and of course James Webb will do a lot of solar system stuff. So yeah, that's fantastic.
That's awesome. So those are all my questions for the day, but I still have another hand raised. So First Lieutenant Deborah, if you can go ahead with your question, please.
Thank you. One of the things we do in Civil Air Patrol is aerospace education for young people. So I'm wondering about your education, your experience. It looks like you're young. How did you get into this position?
Oh, sure. Yeah. So I did my PhD in the UK in Cambridge 2013. Is that right? 2013 till 2017? That's right. And so that was when I finished my PhD. And then I joined the Kepler mission as a support scientist. A support scientist is someone who largely helps the research of others rather than pushing forward their own research. And so that really jammed with me because I really enjoy being part of collaboration and sort of working with big teams and pushing science forward. But I didn't need to be the person like first authoring all the papers. Now the mission is closed out. So for the last couple of years, I've been working on my own research, and I get NASA grants and sort of research with a small team. I have postdoc and different scientists at Ames that I support, and then we do research with archival data to try and get more science out of the archival data.
So would you suggest that young people just get into a good university and head toward a doctorate, head toward astrophysicists?
If you wanted to, so I would say that if anyone wanted to emulate my career, exactly, if anyone wanted to go the same path that I took, I would say the best way forward is to, as early as possible, look into getting really good at computing. And that's like understanding how computers work in a very sort of abstract sense, but also really becoming really good at coding and data analysis. All of my work is essentially sitting at a computer writing research software and data analysis scripts and understanding the data using Python and C code and getting computers to help me get to the real answers that the data are telling me. And so if anyone wanted to follow my exact career path, I would say the best thing to do is to get really good with computers and get really good with coding and data science and that sort of thing. Doing a PhD is probably going to help, but I have friends who work at NASA who do somewhat similar things to me, I think. So having a PhD, if you want to be a research scientist, is probably going to help. Yeah, I think that's where I would start. Also, NASA has a lot of internships if anyone wants to get an understanding of what it's like to be a sort of data scientist and researcher at NASA. And there's internships every spring and summer.
Thank you.
Do we have any other hands raised at this moment? I don't see any other hands raised. So I think we are out of time as well. So we started exactly 1 hour back. So I think this would be a good point to close. Any closing thoughts, Christina? How do you feel about Cerulean Patrol and your presentation today? Any feedback that you want to give us?
No, it's great. Thank you for listening to my talk. It's great just to chat with you guys and hear what you guys think about James Webb. It's great just to show people what James Webb is going to be capable of and share how excited everyone is that it's gonna launch soon and we're going to get some really awesome pictures.
So from behalf of the California wing and Group 2, I'm extremely thankful for your presentation today. So I'm sure this presentation will go a long way in the aspirations of many cadets and senior members who are interested in aerospace. So thank you so much.
Yeah, fantastic. Thanks so much for having me.
Yeah.
Thank you.
Thank you. Bye now.
Bye-bye.
Bye.
Good work, Kailash.
Yeah. Thank you. Have a good night.